Hello my fellow Almonteans, and welcome back to another broadcast from the bunker. Today's hot topic, when I talk about the type of boundaries where these plates meet. We've been talking about the fact that the plates move and how they move. Well, today we're going to talk about the specific action that happens at these boundaries and how that whole process works. Start out in the today's do now, numbers 43 to 45. Meet me there. Okay. Number 43, which planet's orbital shape would be most similar to Jupiter's orbital shape? When you're talking about shape of the orbit, you're not talking about size. Okay, you're not talking about distance from the sun. You're not talking about period of revolution, none of that stuff. It's talking about the shape, so it's referring to eccentricity. If you remember, we had a lab a while back where you guys had to use two thumbtacks, a string, and you had to draw out different orbits with different eccentricities. Well, that's what it's asking about here, the shape. So, most similar to Jupiter, well, that's not something you know off the top of your head. You got to go to the tables, and would have to have a similar eccentricity to Jupiter's eccentricity. Well, take a look. Okay, Jupiter's eccentricity, here's Jupiter, has an eccentricity of 0.048. So, who's closest to that? Well, 0.047, and you're looking at Uranus. Okay, so eccentricity will give an idea of the shape of the orbit. So we said Uranus. Okay, number 44. Major ocean air currents appear to move or curve to the right in the northern hemisphere. That's talking about that Coriolis effect, and that has to do, of course, with the Earth's rotation. So it's got to be the fact that Earth rotates on its axis. I'll show you the reference table that we talked about in class. That is right here, right? So in the northern hemisphere, things curve to the right, and in the southern hemisphere, they curve to the left. And again, that's because of the Earth's rotation at a rate of 15 degrees per hour. Very good. So Earth's rotation, aka Coriolis effect. Okay. And number 45, kind of a strange diagram, right? See a couple of black lines. They're not directly lined up. This is talking about that whole red shift, that Doppler effect, where if things coming closer to you, the wavelength gets compressed and it shifts toward the blue, and if it's going away from you, the wavelength gets stretched and it shifts toward the red. Well, it says, if these lines, reference means standard is in a laboratory, and this, of course, is looking through a fancy telescope. So this is what it would look like if it's not moving. This is what it looks like through the fancy telescope, and it seems to be shifted towards 10 to the -6. Well, we're going to relate that to the reference tables, but if you're shifting that way toward that right, then you're increasing that wavelength there. And the chart you're looking for, is right here. Right, so you're shifting toward that red, toward an increasing wavelength. If that's the case, then it must be moving away from you. Things are getting further apart, and that's your red shift. All right, so shifting toward the red, the galaxy is moving away from you right there. All right, hope that made sense to you. If not, leave a question down in the comment section. I'll get back to you as soon as possible. Okay, so back to the lab here. Excuse me, the lesson. Talking about those plate boundaries today. Okay, let's jump right into it. Quick little clip for you. While you're watching this clip, see if you can answer these two questions. How many different types of plate boundaries are there, and can you name them? Okay, so please pay attention.
Over the course of Earth's history, the flowing of the asthenosphere has caused the planet's crust to break into about 12 large slabs or plates, and several smaller ones. Most plates contain oceanic and continental crust. Plates move relative to one another at speeds of between 2 and 10 centimeters a year. That's about as fast as a human fingernail grows. Plate tectonics helps explain why Earth's surface looks the way it does. It has to do with what happens at the boundaries where plates meet. Divergent boundaries, where plates spread away from each other. Convergent boundaries, where plates push toward one another or collide. Transform boundaries, where plates slide past one another. A well-known transform boundary is the San Andreas Fault, which runs almost the entire length of California. Activity along a fault boundary can cause earthquakes. At convergent or colliding boundaries, one plate generally is forced under the other. This is called subduction. Occasionally, plates crumble, and the folded crust is forced upward. The most striking example of this is the formation of the Himalaya.
Okay, so 2 to 10 centimeters a year. The average is about 3 or 4 centimeters a year, and they said that's about how fast your fingernails grow. This lady is in the Guinness Book of World Record for longest fingernails. I can't imagine what she does as a profession with those nails, right? You really can't do much, but pretty crazy that the plates will move about that same rate. So you don't want to sit around and watch them move, but they're moving. Okay. Identify the characteristic common to most coupled plates. Well, I'm going to isolate these here. You'll notice these all have one thing in common. They're the oceanic plates, and they're going to be made out of basalt. They're going to be denser, darker, right? All those characteristics of basalt. Now I'll highlight the continental plates, and the continents, remember, are mostly made from granite, and that's a felsic rock, less dense, lighter in color, right? They're both igneous rocks. So to summarize, what do they have in common? There you have it, continental crust, those are your characteristics, and the oceanic crust, and there are your characteristics. Okay? All right, make sure you read that through. Just a little recap on the plate tectonic theory. Okay, the mechanism that explains continental drift. Okay, here it is to sum it up. Earth is broken up into tectonic plates. They're slowly moving, constantly. Sometimes they get stuck and they build up energy. And if they get stuck for too long, then when they snap, you get an even bigger earthquake. Driven by the convection of magma in the asthenosphere, aka upper mantle. Okay, and that's the accepted theory today. And these are just some major plate boundary lines. There are minor plate boundary lines. In fact, there is a minor plate not far from Elmont in Manhattan. There are 1 or 2 fault lines, not major like this, but certainly that could cause an earthquake. Okay. So we'll go through the type of boundaries. If you're moving apart like that, you are diverging, right? When you call your buddies up, say, hey, you want to diverge, right? That means go out. In order for it to do that with your hands, what must the convection be doing? Hopefully you've got that down right there. And please draw that in the diagram here. Okay, so the plates are moving away from each other. They're both oceanic in this example. In order to do that, convection must be doing this. In the middle, you have a mid-ocean ridge. That's what that stands for. On land, it would be called a rift valley. Okay, so for your notes, make sure you get it in there. It's divergent. The features are a mid-ocean ridge, a rift valley. You will get earthquakes, but they won't be major generally because nothing's getting stuck. It just kind of pushes out away. And some examples, of course, all of your oceanic ridges, the mid-Atlantic being the most popular we know, but there are, of course, many others. Okay, divergent plate boundary. Another type of boundary, we're not going apart now, we're coming together, we're converging. And of course, this is going to result in much bigger earthquakes and mountain building, as you can see. How do you do that? How do you make plates come together? Well, the magma at some point must be doing this. Right, pushing those plates together. So there you have it. There's your convection. Big mountain range in the middle. that rock's going to get all squeezed and compressed and metamorphosed, right? A lot of metamorphic rock there. Convergent plate boundaries, they're coming together. The features, of course, we got it down there. Big mountains, pretty big earthquakes. And examples over here where India is slamming into Asia here. You get the Himalayan mountains. And, of course, the biggest one would be Mount Everest, right? That example there. Okay. Another type, look, they're both coming together, but now instead of going up, now you have one going down. So that is called convergent sub, meaning to go down, subduction. In order to do that, again, to do this, you have to have this as convection. And you'll end up with this very deep trench here, right? The deepest trenches in the ocean are going to be at these subduction boundaries. So you'll make volcanic mountains at the surface where the lava comes up. In that picture, you see that there. And over here, you'll make very deep trenches, right? The deepest one of them all, the Mariana Trench, something like over 7 miles deep. I mean, that's amazing, folks. Mount Everest is just about 5 miles high. The deepest, and that's the highest mountain on Earth, but the deepest trench is deeper than Everest is high, right? Over 7 miles deep. And the pressure right down there would be amazing. They have made it down there with special equipment. Just recently, James Cameron, maybe you heard of him, director of Avatar, Titanic. Anyway, he funded this expedition to get to the bottom of the Mariana Trench, and he made it. Took some pretty amazing samples and pictures. Okay. But anyways, there you have it, convergent, and it's between two different density plates. Obviously, the denser goes down. The oceanic plate made of basalt is denser than granite, so this would be the ocean and this would be the continent. Or it could be two oceanic plates where the older plate has a lot more sedimentary rock stacked on top, and that makes it heavier and denser, and the older plate goes down and dies, right? It melts. All right. Features, trenches, deep earthquakes, volcanic mountain ranges. You make crazy tsunamis at these subduction zones because the ocean plate snaps and throws the water up, and you get that tsunami wave. All right? The Peru-Chile Trench, an example of this. But any trench, right? The Aleutian Trench, you've heard of the Mariana Trench. They're all going to be these convergent subduction zones. Okay. This similar, this is the ocean one I was just telling you about. This was ocean continent. Ocean is a similar thing, only, you know, this time the older ocean one goes down. You're still going to make your trenches there, only it's in the middle of the ocean. You make this nice island arc. All right, that's a great artist conception of it there. And that would be right up here by the Aleutians. Okay. Again, two oceanic plates. That's both basalt and basalt coming together, but the older one goes down. Okay. And then you get the transform. This is the classic Hollywood earthquake, right, in the San Andreas Fault, right, California, where the plates are trying to slide past each other, but they get stuck, and they build up energy, and eventually they snap. And when they do, the longer they've been stuck, the bigger the energy release is going to be. This is also what happened in Haiti a few years back. That fault that cuts through Haiti and the Dominican Republic there, it got stuck for a while. And when it snapped, I believe that was like an 8, right? Was that around an 8 or so? And a lot of people died because the ground shook so much that the buildings just crumbled, and it was a disaster. Okay? But there you have it. Trying to slide past each other. This is a tricky one to do with your hands. So for this one, you have to have convection going one way and this the other way. And I'm not coordinated enough to do it. Maybe you are. But that's what's going on the bottom there. This is called a fault. All right. Classic example, the San Andreas Fault. Here you have California. It's, you know, almost cut in half by this fault. Okay. All right. All of these boundaries, you do not have to memorize them. They're all on your reference tables. You look at the key on the bottom. It'll tell you what kind of boundary it is. You just got to know where to look. There's that California one we were just talking about. The Mariana Trench, right? The deepest trench in the world right there, right off of the coast of Japan by the Philippine Plate. The Peru-Chile Trench. right? Remember, the trenches often get those big tsunamis because that ocean plate kind of snaps back. All right, so to sum it up, identify and match the image on the appropriate plate boundary. So which type of drawing in your Google Classroom would you match to A? Hopefully you did a transform, right? A sliding past each other boundary. For B, that looks like the center of an ocean. So hopefully you picked one of those mid-ocean ridge type things, a divergent boundary. And for here, the Nazca plate is coming into South America. It's converging and subducting. So hopefully you picked a convergent type of boundary. All right. And we could do this for all over the world. Those are just 3 examples. All right. And of course, can you name those plates? This is just going back to the tectonic chart in the tables. Can you name those plates? Well, run through them, right? You got your Caribbean, where we are, your North American, Eurasian, right? The next one, African. The 5th one here, right? That's your South American plate. And of course, 6, the Indian Australian plate. Okay. So again, just a little background on what's going on in different parts of the world, what type of boundaries there are. If you do have additional questions, again, please leave them in the YouTube section or shoot me a question on Remind. Okay? Have a great day, folks.